Picture this: an explosion so powerful, it outshines entire galaxies. A single cosmic detonation, unleashing more energy in seconds than our Sun will produce in its entire lifetime. These aren't just fireworks, these are the universe's most violent, cataclysmic events, where stars meet their demise in spectacular fashion. Black holes collide with earth-shattering force, and forces beyond comprehension reshape the fabric of space itself. You might think you've seen something explosive, like a supernova or a volcano, but trust me, the universe has ways to make those look like tiny sparks in comparison. Think of it like this: if a regular firework is a pop of light in your backyard, then the events we're about to explore are like detonating a million suns at once. These are the moments when the cosmos reminds us just how small we really are, and yet how thrilling it is to witness its raw power. From hypernova blasts that rip stars apart to gamma-ray bursts so intense they could sterilize planets light years away, these explosions aren't just destructive, they're the engines of creation, scattering the elements that make up everything, including you and me. So buckle up, because over the next 30 facts, we're diving into the most mind-blowing, violent, and awe-inspiring events the universe has to offer. You'll learn how a single dying star can outshine an entire galaxy, how black holes can tear each other apart in a dance of annihilation, and why some explosions are so bright we can see them from the edge of the observable universe. This isn't just science, this is the universe putting on the greatest light show imaginable, and you've got a front row seat. Let's get started. Fact 1: Supernovas, the universe's ultimate firecrackers. These aren't just stars burning out quietly, they're going out with a bang so massive it can outshine an entire galaxy for weeks. To understand the sheer scale of these explosions, picture our Sun, a blazing ball of energy that's powered our solar system for billions of years. Now imagine a star, dozens or even hundreds of times more massive, collapsing in on itself in a fraction of a second. The shockwave alone flings debris outward at speeds reaching tens of millions of kilometers per hour, releasing as much energy as our Sun will generate in its entire 10 billion-year lifetime, all in a single, catastrophic instant. This cosmic detonation doesn't just light up the darkness, it reshapes it. When a supernova erupts, it scatters heavy elements like iron, gold, and uranium across space, seeding future generations of stars, planets, and even life itself. That's right, the iron in your blood, the gold in your jewelry, and the uranium deep within Earth's crust were all forged in the heart of these stellar explosions billions of years ago. One of the most famous examples is SN 1054, the supernova that birthed the Crab Nebula. Chinese astronomers recorded it as a new star so bright it was visible in broad daylight for weeks. Today, we can still see the aftermath, a swirling cloud of gas and dust expanding outward like a celestial fingerprint. But how does a star reach this explosive breaking point? It all comes down to a battle between gravity and nuclear fire. For millions of years, a massive star fuses lighter elements into heavier ones, buying time against the crushing weight of its own gravity. But when its core runs out of fuel, gravity wins, and in a single, violent moment, the star's core collapses. The outer layers rebound off this collapse in a shockwave so powerful it rips the star apart. Some supernovas even leave behind cosmic zombies, neutron stars spinning at dizzying speeds, or black holes with gravitational pulls so strong not even light can escape. It's a reminder that even in destruction, the universe is always building something new. Fact 2: Hypernovas, where supernovas crank the dial to 11. If a regular supernova is a firecracker, then a hypernova is like detonating an entire warehouse of dynamite at once. We're talking about stellar explosions so extreme, they unleash 100 times more energy than their already mind-blowing counterparts. These aren't just stars dying, they're stars self-destructing in the most spectacular way imaginable. leaving behind cosmic scars we can still detect billions of years later. The secret behind these ultraviolet explosions lies in the stars that create them. Picture a star so massive, so unstable, that it's practically a ticking time bomb. When these behemoths, often dozens of times heavier than our Sun, reach the end of their lives, they don't just collapse. They implode with such ferocity that their cores don't just form neutron stars, they snap straight into black holes. And here's where things get even wilder. As the star's outer layers come crashing down, they don't just rebound in a spherical explosion. Instead, they get funneled into jets of ultra-high-energy material screaming outward at nearly the speed of light. These jets are so focused, so intense, that they punch through the remnants of the star like cosmic blowtorches, creating what we see as gamma-ray bursts, some of the brightest flashes of light in the universe. Scientists believe hypernovas might be the cosmic engines behind long gamma-ray bursts, those mysterious flashes of energy that can outshine entire galaxies for minutes at a time. When one of these jets happens to point directly at Earth, we catch a fleeting glimpse of the aftermath, a beacon of destruction visible across billions of light years. But there's a twist. These explosions don't just destroy. Like their smaller supernova cousins, hypernovas are cosmic forges, blasting heavier elements like gold and platinum into space. In a way, every piece of jewelry you've ever seen owes its existence to the apocalyptic deaths of stars far more violent than our own Sun. The aftermath of a hypernova is just as extreme as the explosion itself. Instead of leaving behind a spinning neutron star, these events often birth black holes with gravitational pulls so strong they warp space-time itself. Some researchers even speculate that hypernovas could be the origin stories for some of the universe's most mysterious phenomena, like those elusive intermediate mass black holes, which sit somewhere between the small ones formed by regular supernovas and the supermassive monsters lurking in galactic cores. It's a staggering thought. A single star's death might plant the seeds for an entirely new cosmic predator. Fact 3. Gamma-ray bursts, the universe's most lethal flashes of light. These aren't just bright, they're apocalyptic. In less time than it takes to blink, a single burst can unleash more energy than our Sun will radiate over its entire 10 billion-year lifespan. Imagine squeezing all that power into a beam narrower than a pencil's width, screaming across the cosmos at the speed of light. If one of these beams happened to hit Earth head-on, even from thousands of light years away, it could strip our atmosphere of ozone in seconds, triggering mass extinctions and bathe the planet in deadly radiation. The terrifying part, we've seen these bursts happen. In 1967, satellites designed to monitor nuclear tests unexpectedly picked up flashes of gamma rays coming from deep space. At first, scientists thought they might be secret weapons tests until they realized the bursts were coming from every direction, billions of light years away. Today, we know these flashes are the death cries of massive stars or the violent mergers of neutron stars, events so catastrophic they warp space-time itself. Some bursts last only milliseconds, while others linger for minutes, shining with the brightness of 1,000,000 trillion suns. The energy is so concentrated that if you could harness just 1 second's worth, it could power human civilization for centuries. Detection is another challenge entirely. Because gamma rays don't penetrate Earth's atmosphere, we rely on satellites like NASA's a Swift Observatory and Fermi Gamma Ray Space Telescope to catch these fleeting cosmic fireworks. When a burst is detected, telescopes worldwide swivel into action, capturing the fading afterglow in visible light, X-rays, and radio waves. These observations have revealed that some bursts come from galaxies in the early universe, meaning we're seeing explosions that happened when the cosmos was just a fraction of its current age. But here's the twist: gamma-ray bursts might actually be the universe's way of recycling. The same cataclysmic events that create them also forge heavy elements like gold and platinum, scattering them across space to one day become part of new stars, planets, and even life. So while these bursts are terrifying in their power, they're also a reminder that destruction and creation are two sides of the same cosmic coin. And thanks to our ever-watchful telescopes, we get to witness these fleeting moments of chaos, billions of years after they first tore through the darkness. Fact 4: kilonovas, the universe's ultimate gold factories. Imagine two dead stars, each so dense a teaspoon of their material would weigh 1 billion tons, spiraling toward each other at nearly the speed of light. When they finally collide, the impact is so violent it ripples the fabric of space-time itself and sprays the cosmos with enough gold, platinum, and other heavy elements to coat entire planets. This isn't just a collision, it's a cosmic alchemist's dream, transforming the remnants of dead stars into the very elements that make up our most precious metals. The historic detection in 2017 changed everything. For the first time, astronomers didn't just see a kilonova, they heard it. The Laser Interferometer Gravitational Wave Observatory, or LIGO, picked up the faint tremors of space itself warping as two neutron stars circled each other in a death spiral. Moments later, telescopes around the world caught a flash of light, a brilliant burst of gamma rays followed by a glowing afterburn that radiated across the electromagnetic spectrum. This wasn't just a breakthrough, it was a new era of astronomy where scientists could listen to the universe's vibrations while simultaneously watching the fireworks. What makes kilonovas so special isn't just their violence, it's what they leave behind. In the swirling debris of these collisions, neutrons bombard atomic nuclei at unimaginable speeds, forging elements heavier than iron in a process called rapid neutron capture. Picture a cosmic soup of particles smashing together so forcefully they stick, creating gold, platinum, and even uranium in seconds. Scientists estimate a single kilonova can produce hundreds of Earth masses worth of these precious metals, scattering them across galaxies to later become part of asteroids, planets, and even the rings on your fingers. The aftermath of a kilonova is just as fascinating as the explosion itself. Sometimes the collision leaves behind a hypermassive neutron star, a temporary monster so dense it defies physics before it collapses into a black hole. Other times, the debris forms an accretion disk of superheated material that glows for days, a telltale sign of the heavy elements being born in the chaos. What's truly staggering is how common these events might be. Before 2017, kilonovas were purely theoretical. Now, we know they're happening all across the universe, silently seeding galaxies with the ingredients for future solar systems. Here's the wildest part: we're made of this stuff too. The gold in your jewelry, the platinum in your electronics, even the uranium deep inside the Earth. All of it was likely forged in the heart of a kilonova billions of years ago. These cataclysmic events aren't just destructive, they're the universe's way of recycling star stuff into the building blocks of everything we know. And thanks to advancements in gravitational wave astronomy, we're finally unlocking the secrets of these cosmic forges, one collision at a time. Fact 5: Quasar outbursts, the universe's ultimate black hole power plants. Imagine an object so bright, it outshines 1,000 galaxies combined, yet it fits inside a space smaller than our solar system. These aren't stars, they're quasars, the luminous hearts of distant galaxies where supermassive black holes feast on cosmic gas and dust with such ferocity. They light up the cosmos like beacons across billions of light years. When astronomers first stumbled upon quasars in the 1960s, they were baffled. These points of light looked like stars, but their spectra told a different story. They were racing away from us at unimaginable speeds, meaning they had to be billions of light years distant. The only explanation: these quasi-stellar objects were producing incomprehensible amounts of energy. We now know quasars are the blazing signatures of supermassive black holes, some weighing billions of times more than our Sun, gorging on swirling disks of superheated material. As gas spirals inward at nearly light speed, friction heats it to millions of degrees, blasting out radiation across the entire electromagnetic spectrum. The scale of these outbursts defies belief. A single quasar can shine with the brightness of 10 trillion suns, its light so intense it drowns out every star in its host galaxy. The energy isn't just coming from the black hole itself, it's the dying scream of matter being shredded apart before vanishing beyond the event horizon. Some quasars even shoot out jets of plasma thousands of light years long, like cosmic blowtorches carving through intergalactic space. What's truly wild is how common these monsters once were. In the early universe, quasars lit up like fireworks as galaxies formed and black holes feasted on abundant gas. Today, most have gone silent, their fuel exhausted. But their legacy lives on. Every massive galaxy, including our own Milky Way, likely hosted a quasar in its youth. The supermassive black holes they left behind still lurk in galactic centers, waiting for their next cosmic meal. Here's the twist: quasars aren't just destructive. Their intense radiation can shape entire galaxies, halting star formation by blowing away gas clouds. In a way, these ancient power plants helped sculpt the universe we see today, their light carrying clues about how galaxies grew and evolved over billions of years. And thanks to modern telescopes, we're still uncovering their secrets, one dazzling outburst at a time. Fact 6: Tidal disruption events, the universe's most extreme cosmic shredders. Picture a star minding its own business, drifting too close to a lurking black hole. In an instant, the star's life takes a horrifying turn. The black hole's gravity grabs hold, stretching the star like taffy until it's nothing more than a thin, screaming stream of superheated gas, a process so violent, astronomers call it spaghettification. But this isn't just destruction, it's a full-blown cosmic light show, as the star's remains swirl into a glowing disk around the black hole, blasting out enough energy to outshine entire galaxies. One of the most jaw-dropping examples happened in 2015, when astronomers spotted an explosion called Assassin 15LH. At first, they thought it was just another supernova, until they realized it was 200 times brighter than any stellar explosion ever recorded. This wasn't a star collapsing on itself. This was a star being devoured alive by a supermassive black hole. The sheer intensity of the light defied expectations, forcing scientists to rethink what happens when these cosmic monsters feed. Some theories suggest the black hole might have been spinning so fast it whipped the star's debris into a frenzy, or perhaps the star was unusually massive, turning its death into an all-you-can-eat buffet for the black hole. What makes tidal disruption events so fascinating isn't just their violence, it's how unpredictable they are. Unlike supernovas, which follow a roughly predictable script, these events depend entirely on the star's size, the black hole's hunger, and even the angle at which the star approaches. Sometimes the star gets torn apart in a single, dramatic pass. Other times it might survive multiple orbits, only to have layers ripped away like peeling an onion in slow motion. The debris that doesn't vanish beyond the event horizon gets superheated to millions of degrees, creating a temporary beacon of X-rays and ultraviolet light visible halfway across the observable universe. The aftermath is just as wild. Some of the star's material gets flung away entirely, forming a glowing halo around the black hole. The rest spirals inward, feeding the beast and powering jets of plasma that scream into space at relativistic speeds. These events are rare, happening maybe once every 10,000 years in a typical galaxy, but when they do, they offer scientists a front-row seat to the messy, chaotic physics of black holes in action. And with new telescopes scanning the skies every night, we're catching more of these cosmic snack sessions than ever before. Who knows what other surprises are lurking in the darkness, waiting for a star to wander just a little too close. Fact 7: Active galactic nuclei, the universe's most destructive tornadoes. Deep in the hearts of certain galaxies, cosmic storms rage with such intensity, they make hurricanes look like gentle breezes. These aren't just energetic cores, they're maelstroms of superheated gas and magnetic fields, swirling around supermassive black holes with the fury of a billion suns. And when these monsters awaken, they unleash jets of plasma so powerful they could vaporize entire solar systems in their path. The sheer scale of these outbursts is almost beyond comprehension. Imagine taking the energy of 1,000,000 supernovas and focusing it into twin beams narrower than a solar system, screaming across space at 99% the speed of light. That's the power of an active galactic nucleus, or AN. For decades, astronomers puzzled over these bizarre objects, bright spots at galaxy centers flickering like cosmic strobe lights. We now know they're black holes on feeding frenzies, devouring so much material that the friction alone heats gas to billions of degrees, lighting up the cosmos like a beacon. But the real showstopper is those jets. Picture a black hole spinning so fast, it twists space-time around it like a whirlpool, channeling magnetic fields into cosmic particle accelerators. Electrons get whipped to near light speed, shooting out in opposite directions for thousands, sometimes millions of light years. These jets carve through galaxies like celestial blowtorches, creating shock waves that trigger or halt star formation in their wake. Some even punch straight out of their host galaxies, creating towering structures called radio lobes that glow with the energy of ancient outbursts. Here's the twist: active galactic nuclei aren't just destroyers. Their intense radiation can heat surrounding gas so much, it prevents new stars from forming, essentially putting galaxies into early retirement. But they also seed the cosmos with heavy elements forged in their accretion disks, spreading the ingredients for future planets and life. And because their light takes billions of years to reach us, studying AGNs is like looking back in time, watching how galaxies and their black holes evolved together. One of the most famous examples lies in the galaxy M87, where the Event Horizon Telescope captured the first ever image of a black hole's shadow. The same black hole powers a jet stretching 5,000 light-years into space, a relic of past outbursts. What's staggering is how common these engines once were in the early universe before gas supplies dwindled. AGNs lit up like cosmic lighthouses, shaping the growth of galaxies around them. Today, our Milky Way's black hole is quiet, but who knows when it might wake up for another meal, reminding us just how dynamic and dangerous the universe can be. Fact 8. Magnetar flares, the universe's most terrifying electromagnetic tantrums. These aren't just neutron stars, they're cosmic monsters with magnetic fields so strong they could strip the information off every credit card on Earth from halfway across the galaxy. And when one of these magnetic leviathans cracks under the pressure, the result is an explosion of energy so intense, it briefly outshines every star in the Milky Way combined. Take the flare of December 27, 2004, a date astronomers won't soon forget. From 50,000 light-years away, a magnetar called SGR 1820-20 let loose a scream of gamma rays and X-rays so powerful, it actually compressed Earth's upper atmosphere, bouncing radio waves back to the surface like a cosmic ping-pong ball. Satellites designed to detect nuclear explosions went haywire, their circuits overwhelmed by what might as well have been an interstellar EMP. All this from an object no bigger than a city, flaring for just 0.2 of a second. What makes magnetars so volatile? Picture a neutron star, already one of the densest objects in existence, spun up to nightmare specifications. During a supernova, some neutron stars inherit magnetic fields 1,000 trillion times stronger than Earth. These fields are so intense, they warp the very atoms on the star's surface, twisting electron orbits into impossible shapes. Over time, the crust of the magnetar builds up stress like a tectonic plate until it fractures in a starquake. The energy release is apocalyptic. Magnetic field lines snap and reconnect, accelerating particles to near light speed in a fireball of X-rays and gamma rays. For a brief moment, the flare can outshine every gamma-ray source in the galaxy, including black holes and quasars. And because magnetars rotate rapidly, these outbursts often come in precise, repeating bursts like a cosmic lighthouse gone haywire. The most unsettling part, we know these flares have left scars on Earth before. Tree ring data suggests a magnetar flare around the year 775 AD bathed our planet in enough radiation to leave traces in ancient cedar trees. If a similar flare happened today, it could knock out satellites, disrupt power grids, and bathe astronauts in deadly radiation. Yet these same terrifying outbursts might also solve cosmic mysteries. Some scientists speculate that magnetar flares could be the source of fast radio bursts, those enigmatic intergalactic signals that have puzzled astronomers for years. What's truly humbling is the scale of these events. A single magnetar flare can release more energy than our Sun will emit in 100,000 years, all from an object with the diameter of Manhattan. And with dozens of known magnetars lurking in our galaxy, it's only a matter of time before another one reminds us just how small we really are in the face of nature's most extreme forces. Fact 9. Solar flares, our very own star's explosive mood swings. While we've been marveling at cosmic detonations light years away, the Sun reminds us it doesn't need distance to pack a punch. A single solar flare can unleash the energy of 1 million hydrogen bombs in minutes, hurling charged particles toward Earth at speeds topping 1 million miles per hour. And when these storms hit, they don't just light up the sky, they can fry satellites, knock out power grids, and even reroute airplanes. Take the Carrington event of 1859, the solar storm by which all others are measured. On September 1st, British astronomer Richard Carrington sketched a cluster of blindingly bright spots on the Sun's surface, a flare so intense its auroras lit up the night sky as far south as Cuba and Hawaii. But the real chaos unfolded along the world's telegraph lines. Operators reported sparks leaping from their equipment, papers catching fire, and machines somehow transmitting messages even after being disconnected from power. In some cases, the aurora-induced currents in the wires were so strong, telegraph operators could send messages without batteries, powered solely by the storm itself. Modern simulations suggest the Carrington flare unleashed roughly 10 billion tons of charged particles, a coronal mass ejection moving fast enough to reach Earth in just 18 hours instead of the usual 3 to 5 days. If a storm like that hit today, the consequences could be catastrophic. Imagine entire continents plunged into darkness as transformers overload and fail. GPS signals disrupted, leaving ships and planes navigationally blind. Satellites, from communication networks to weather monitors, crippled by radiation. One study estimated the global economic impact could exceed $2 trillion, with full recovery taking years. Yet solar flares aren't just agents of chaos, they're also dazzling reminders of our star's dynamic nature. The process begins with twisted magnetic field lines on the Sun's surface, storing energy like wound-up rubber bands. When these lines snap and reconnect, they release explosions of X-rays and ultraviolet light, followed by those planet-menacing particle clouds. And while most flares are harmless, the Sun cycles through periods of hyperactivity every 11 years, raising the odds of another Carrington-level event. What's fascinating is how unprepared we still are. During a near miss in 2012, a coronal mass ejection missed Earth by just 9 days, a cosmic warning shot. Space agencies now monitor the Sun around the clock, and engineers harden power grids against surges, but the truth remains. We're one well-aimed solar tantrum away from a technological wake-up call. The same forces that paint our skies with auroras could also send us back to the pre-digital age, proof that even our local star has a temper worth respecting. Fact 10. Coronal mass ejections, the Sun's ultimate tantrums. While solar flares light up the sky with bursts of radiation, it's these titanic plasma storms that pose the real danger to our tech-dependent world. Picture a billion-ton cloud of charged particles, hotter than lava and moving at speeds topping several million miles per hour, hurled straight toward Earth with the force of a cosmic hurricane. These aren't just space weather, they're solar tsunamis capable of frying power grids, scrambling satellites, and turning modern life upside down in a matter of hours. The mechanics behind these eruptions are as fascinating as they are terrifying. Deep in the sun's corona, its scorching outer atmosphere, magnetic fields twist and knot like rubber bands stretched to their breaking point. When the tension becomes too much, they snap, flinging a chunk of the sun's plasma into space. Unlike the focused energy of a flare, a coronal mass ejection is a sprawling wave of destruction, sometimes wider than the sun itself. If Earth happens to be in the crosshairs, that wave can reach us in as little as 15 hours, slamming into our planet's magnetic field like a battering ram. History offers chilling examples of what happens when these storms hit. The Carrington event of 1859 wasn't just a flare, it was a coronal mass ejection of unprecedented scale, sparking auroras so bright, people in the northeastern United States could read newspapers by their glow at midnight. But the real damage came from the invisible currents surging through telegraph wires, shocking operators and setting equipment ablaze. Fast forward to 1989, when a far weaker storm blacked out the entire province of Quebec in seconds, leaving 6 million people in the dark for 9 hours as overloaded transformers exploded like firecrackers. Today, the stakes are infinitely higher. A Carrington-level event now could collapse power grids across continents, disrupt global communications, and knock out satellites we rely on for everything from banking to weather forecasting. The economic fallout could eclipse $2 trillion, with full recovery taking years. That's why NASA and other space agencies keep constant watch with satellites like the Solar Dynamics Observatory and the Deep Space Climate Observatory. These silent sentinels orbit between us and the Sun, giving engineers as much as 48 hours warning to shut down vulnerable systems before a storm hits. Yet for all their destructive potential, coronal mass ejections also paint our skies with breathtaking auroras, proof that even the sun's fury can create beauty. And they serve as a humbling reminder, no matter how advanced our technology becomes, we're still at the mercy of our star's whims. The sun doesn't need supernovas or black holes to remind us of its power. Sometimes all it takes is one well-aimed burst of plasma to show just how fragile our electrified world really is. Fact 11. Rogue black holes, the invisible drifters of the cosmos. Unlike their supermassive cousins anchored at galactic centers, these lone wolves roam the voids between stars, untethered and undetectable until something crosses their path. Picture a black hole with the mass of 20 suns, barreling through space at hundreds of kilometers per second, its gravitational wake bending starlight and shredding any system unlucky enough to cross its path. These aren't just theoretical oddities, they're cosmic ghosts, and they might be far more common than we ever imagined. The chilling reality is that spotting a rogue black hole is nearly impossible without a victim. Unlike active black holes that glow as they devour gas, these wanderers drift in darkness, betraying their presence only through subtle distortions. In 2011, astronomers witnessed a star suddenly brightening and warping in a way that defied normal explanations, a phenomenon called gravitational microlensing. The culprit, a rogue black hole roughly 7 times the mass of our Sun, passing between Earth and the star like a cosmic sniper. It was the first confirmed detection of its kind, proving these solitary predators aren't just hypothetical. How do these black holes end up alone? One theory points to violent beginnings. When 2 galaxies merge, their central supermassive black holes can slingshot stars and even smaller black holes into deep space during the chaotic dance. Others might be born rogue stellar black holes flung away by asymmetric supernova explosions, sent careening like cosmic billiard balls. Some simulations suggest thousands could be lurking in the Milky Way's halo, remnants of smaller galaxies torn apart and absorbed by ours over billions of years. The numbers are staggering. A recent study estimated our galaxy might host as many as 100 million rogue black holes, outnumbering their star-bound counterparts 10 to 1. Most would be impossible to detect unless they disturb a nearby star or cloud of gas. But when they do, the results are catastrophic. A close encounter could fling planets from their orbits, rip stars apart with tidal forces, or even redirect entire star clusters like a gravitational bulldozer. Here's the twist: these nomads might hold clues to some of the universe's biggest mysteries. Their lensing effects could help map dark matter, and their mergers might explain some of the gravitational waves we've detected. Some scientists even speculate they could serve as accidental space highways, slingshotting civilizations if they exist across vast distances. For now, they remain shadowy enigmas, a reminder that even in the apparent emptiness of space, danger could be lurking just beyond the light. Fact 12. Vacuum decay, the universe's most existential off-switch. Imagine a single, microscopic bubble forming somewhere in the cosmos, its walls expanding at the speed of light, rewriting the very laws of physics as they go. One moment, reality operates as we know it: gravity pulls, light travels, atoms bond. The next, every fundamental force and particle in existence suddenly obeys new rules, unraveling stars, planets, and life itself in an instant. This isn't science fiction. It's a theoretical disaster scenario so absolute, even black holes wouldn't survive it. The terrifying premise hinges on a cosmic gamble that our universe isn't in its true lowest energy state. Think of it like a marble resting in a valley, but that valley might actually sit on a mountainside. If quantum fluctuations ever knock that marble over the edge, it could trigger a catastrophic phase transition, a bubble of true vacuum where physics operates differently. The moment this bubble forms, its boundaries would expand uncontrollably, converting everything in their path into this new, alien reality. The shockwave wouldn't just destroy matter, it would erase the rules that allow matter to exist in the first place. What's chilling is how little warning we'd get. The bubble could form anywhere, in a distant galaxy or right next to Earth, and we'd have zero time to react. The moment light from the event reached us, the wave itself would already be here, rewriting atomic bonds before our neurons could even process the danger. The universe wouldn't so much end as reconfigure itself into something utterly unrecognizable. Yet physicists sleep soundly for good reason. While the math allows for vacuum decay, our universe's stability over 13.8 billion years suggests we're probably in a deep, safe energy valley. Particle colliders like the Large Hadron Collider have probed extreme energies without triggering catastrophe, and cosmic rays bombard Earth with far higher energies than we can create, all without incident. Still, the idea captivates scientists because it touches on existential questions: why our universe has the laws it does, and whether they're as permanent as they seem. The irony: if vacuum decay ever happened, we wouldn't just be witnessing the end of our universe, we'd be creating a new one with entirely different rules, a cosmic reset button pressed by random quantum chance. It's a humbling reminder that for all our knowledge, the universe might still hold surprises we can't even imagine. And that's what makes this doomsday scenario so fascinating. Not because it's likely, but because it forces us to confront just how little we truly understand about the fabric of reality itself. Fact 13. The Big Bang, the mother of all cosmic explosions. This wasn't just a bang, it was the ultimate birth cry of reality itself, a firestorm so intense it forged space, time, and every atom in existence. Picture a singularity smaller than a grain of sand, hotter than a trillion suns, suddenly expanding faster than light itself. In less time than it takes to blink, the universe grew from subatomic to cosmic scales, a process called inflation that still baffles physicists today. The early moments read like a cosmic recipe for chaos. For the first microsecond, everything was a seething soup of quarks and gluons, particles so energetic they couldn't even stick together to form protons. Then, as the universe cooled, these particles finally clumped into atoms, releasing a flash of light so powerful its afterglow still lingers today. We call this the cosmic microwave background, and it's literally the oldest photograph in existence, a snapshot of the universe when it was just 380,000 years old. What's mind-blowing is how we've pieced this story together. In 1965, two radio astronomers accidentally discovered the cosmic microwave background while troubleshooting antenna noise. That static turned out to be the cooled remnants of the Big Bang's light, stretched over 13.8 billion years into faint microwaves. Today, satellites like Planck have mapped this afterglow in exquisite detail, revealing temperature fluctuations that became the blueprints for galaxies. But the Big Bang wasn't silent. Its echoes might still reverberate through space. Some theories predict gravitational waves from inflation itself, ripples in space-time so ancient they'd predate even the cosmic microwave background. Experiments are hunting for these whispers, hoping to glimpse the universe's first trillionth of a second. Meanwhile, particle colliders like the Large Hadron Collider recreate quark-gluon plasma, letting us study the universe's primordial state in miniature. The wildest twist, the Big Bang might not have been the beginning. Some models suggest it was a rebound from a previous universe's collapse, while others propose an eternal multiverse where bang after bang spawns new realities. One thing's certain: every atom in your body, every star in the sky, and even the darkness between them all trace back to this explosive genesis. And with each new discovery, we're rewriting the story of how everything, literally everything, came to be. Fact 14. Dark energy, the universe's silent explosion. Unlike the cataclysmic blasts we've explored so far, this one doesn't tear through stars or light up the cosmos. Instead, it's an invisible, relentless force stretching space itself apart. An expansion so baffling it earned scientists the 2011 Nobel Prize in Physics for its discovery. Imagine blowing up a balloon with unseen hands, but instead of slowing down, the balloon inflates faster and faster with each passing second. That's dark energy in action, rewriting the destiny of the entire universe. The story begins in the 1990s when astronomers made a discovery that turned cosmology upside down. By studying distant supernovas as cosmic mile markers, two independent teams expected to measure how much the universe's expansion was slowing due to gravity. Instead, they found the opposite. The explosions were fainter than predicted, meaning space had stretched more than anyone anticipated. The shocking conclusion: some mysterious force was overpowering gravity, accelerating the universe's expansion. Overnight, dark energy went from theoretical curiosity to one of the biggest mysteries in science. What makes dark energy so unsettling is how little we understand it. The leading theory suggests it's a property of space itself, what Einstein once called the cosmological constant, a kind of anti-gravity woven into the vacuum. Other ideas propose undiscovered fields or even modifications to Einstein's theory of gravity. But the numbers defy intuition. Dark energy makes up roughly 68% of the universe's total energy, yet its effects only became noticeable about 5 billion years ago, when the cosmos grew large enough for its push to outweigh gravity's pull. The consequences are staggering. If dark energy continues unchecked, it could lead to a big freeze, where galaxies grow so distant from one another that future civilizations will see nothing beyond their own stellar neighborhood. Stars will burn out, black holes will evaporate, and the universe will fade into cold, empty darkness. But there's a twist. Some models suggest dark energy might strengthen over time, leading to a big rip where even atoms are torn apart by runaway expansion. What's truly humbling is how recent this discovery is. For centuries, we assumed the universe's expansion was slowing. Now we know it's speeding up, driven by something invisible that defies all our expectations. And with new telescopes like the Vera Rubin Observatory coming online, we're on the verge of probing dark energy's secrets like never before. One thing's certain: this silent explosion is the most powerful force in the cosmos, and it's rewriting the universe's future in ways we're only beginning to comprehend. Fact 15. Cosmic inflation, the universe's most extreme growth spurt. Forget about the Big Bang's fireball. The real showstopper happened in the first trillionth of a second, when the entire cosmos likely expanded faster than the speed of light. Picture a space smaller than a proton blowing up to the size of a grapefruit in less time than it takes light to cross an atom. This wasn't just expansion, it was space-time itself stretching at a rate so absurd, it makes rockets look like snails. The evidence for this wild idea comes from an unlikely place: the cosmic microwave background, that faint afterglow of the Big Bang we mentioned earlier. When scientists mapped its temperature with satellites like Planck, they noticed something peculiar. The microwave sky is almost perfectly uniform, with temperature variations of just 1 part in 100,000. That level of smoothness shouldn't be possible unless regions billions of light-years apart were once close enough to equalize their heat, something only achievable if space ballooned faster than light could traverse it. Here's where it gets even stranger. Quantum fluctuations during inflation, tiny ripples in the fabric of reality got stretched to cosmic scales, becoming the seeds for all structure in the universe. Those microscopic wrinkles eventually grew into galaxies, galaxy clusters, and the vast cosmic web we see today. Without inflation, the cosmos might have remained a featureless sea of particles. Instead, those imperfections became the blueprints for everything from stars to planets to life itself. The theory also solves cosmic headaches like the horizon problem. Why does the universe look the same in all directions when light hasn't had time to travel between distant regions? Inflation answers this by suggesting everything we see was once crammed into a tiny, ultra-connected space before expanding unimaginably fast. It's like blowing up a single puzzle piece to cover a football field. The patterns stay consistent because they originated when all the pieces were touching. Yet mysteries remain. What triggered inflation? What stopped it? Some theories suggest it was a phase transition, like water freezing into ice, where the universe's energy state suddenly shifted. Others propose inflation never fully ended, that our universe is just one bubble in an eternally inflating multiverse, where new bubble universes pop into existence endlessly. Whatever the truth, one thing's certain: those first moments of exponential growth didn't just shape the universe, they wrote the rulebook for everything that followed, from the first stars to the planets that orbit them. And buried in that faint microwave static are clues waiting to rewrite our understanding of existence itself. Fact 16. The Big Rip, the universe's most gruesome farewell. Forget fading into darkness or collapsing in on itself. This is an ending where the cosmos gets torn apart atom by atom, its very fabric shredded by dark energy's unrelenting grip. Picture a force so powerful it overcomes gravity, electromagnetism, even the nuclear bonds holding matter together. Galaxies would be the first to go, ripped from one another as space stretches faster than light can bridge the gaps. Stars would follow, their planets scattered like cosmic confetti. Then, in the final moments, atoms themselves would unravel, protons and electrons wrenched apart as if the universe itself forgot how to hold things together. The math behind this nightmare comes down to dark energy's sinister secret. It might not just accelerate the universe's expansion, but grow stronger over time. Current estimates suggest that if this phantom energy scenario is real, the countdown to total dissolution could begin in roughly 22 billion years. First, galaxy clusters would vanish beyond each other's horizons in about 60 billion years. Stars within galaxies would drift apart 20 million years later. Just months before doomsday, solar systems would disintegrate. In the last terrifying minutes, planets and stars would burst apart as the forces binding them succumb to stretching space. The final microseconds would see atoms and nuclei shredded, leaving behind a cold, empty void where the universe once thrived. What's chilling is how little say physics has in this scenario. Unlike the Big Crunch, where gravity might pull everything back together, or the heat death of the universe where entropy wins, the Big Rip doesn't negotiate. Dark energy's hypothetical strengthening would mean even quantum forces are powerless against it. Some theories suggest the rip could be so absolute, it might prevent new universes from forming in the aftermath, leaving nothing but a featureless expanse where time and space lose all meaning. Yet there's a strange comfort in the sheer scale of this catastrophe. Humanity will likely be long gone before the first warning signs emerge, if we even survive the next billion years. And for now, dark energy's true nature remains one of cosmology's greatest mysteries. Current observations show it behaving as a constant force, not growing stronger. But the possibility lingers, a reminder that the universe's ultimate fate might be less about fading away and more about coming violently undone. The same force accelerating galaxies apart today could one day turn on existence itself, proving that even the vacuum of space isn't as empty or as peaceful as it seems. Fact 17. Pair instability supernova, the cosmic vanishing act where stars don't just die, they erase themselves from existence. These aren't your typical supernovas leaving behind neutron stars or black holes. These are explosions so total, so utterly catastrophic, that they blast every last trace of the star into space, leaving nothing behind but an echo of light. Picture a star so massive, its core becomes a runaway nuclear furnace, producing energy so intense that matter and antimatter spontaneously materialize from pure radiation. The result, a detonation powerful enough to vaporize the entire star down to its last atom. The physics behind these events reads like something from a sci-fi novel. Stars between 100 and 300 times the mass of our Sun reach a point where their cores get so hot, gamma rays, the most energetic form of light, start converting into electron-positron pairs. This sudden switch from radiation to particles removes the outward pressure that's been holding the star up against gravity's crushing grip. In an instant, the core collapses, igniting a runaway thermonuclear explosion that doesn't just rip the star apart, it annihilates it. No black hole, no neutron star, just a colossal fireball scattering stardust across the cosmos. These explosions might seem rare, but they played a starring role in shaping the early universe. In the cosmic dark ages before galaxies as we know them existed, pair instability supernova were likely far more common. Their sheer violence seeded pristine space with heavy elements like oxygen, carbon, and silicon, the raw materials for future stars, planets, and even life. Some scientists speculate these blasts might explain why early galaxies have chemical fingerprints so different from modern ones. The first stars weren't just bigger and brighter, they died in ways we'll never see in today's universe. One of the most intriguing candidates for a pair instability supernova popped up in 2007 when astronomers spotted a blast called SN 2006 Gi. It was 10 times brighter than a normal supernova and lasted 3 times longer, exactly what you'd expect if a monstrous star had completely disintegrated. The light curve, the elemental signatures, even the lingering glow all pointed to a star that had essentially turned itself inside out. Here's the twist, these explosions might be the reason we don't see stars above a certain size today. Pair instability supernova could have acted as a cosmic weight limit, capping how large stars could grow in the early universe by ensuring the most massive ones never left behind black holes to grow even larger. It's a reminder that destruction can be creative. These vanishing acts didn't just end stars, they set the stage for everything that came after. Fact 18. Pulsar glitches, the universe's most precise timekeepers with an occasional rebellious streak. These ultra-dense neutron stars, the remnants of supernova explosions, spin with such regularity that their rhythmic pulses rival atomic clocks until suddenly, without warning, they speed up like a cosmic engine revving out of nowhere. These aren't just minor stutters, they're violent rearrangements of stellar material, releasing enough energy in seconds to power human civilization for centuries. Take the Vela pulsar, one of the most notorious glitches we've observed. Normally, it spins 11 times per second, beaming radiation like a lighthouse with metronome precision. But every few years, without fail, its rotation jumps, gaining an extra fraction of a spin per second in a celestial hiccup that defies expectations. The forces behind these events are staggering. Picture a neutron star's crust, a mile-thick shell of iron nuclei packed so tightly they form a crystalline lattice, suddenly cracking under immense stress. Meanwhile, the superfluid core beneath, frictionless and swirling at blinding speeds, transfers its energy outward in a sudden surge, like water sloshing in a spinning bucket suddenly hitting the sides. What makes these glitches so fascinating isn't just their unpredictability, it's what they reveal about the extreme physics inside neutron stars. The angular momentum stored in that superfluid core is immense, and when a fraction of it couples to the crust, the star's spin rate lurches forward like a paused record skipping ahead. Some glitches are tiny, barely noticeable. Others, like the one observed in the Crab pulsar in 2019, can alter the star's rotation by a full microsecond per day, a colossal shift on cosmic scales. The sheer energy released during these events is mind-bending. A single glitch can dissipate enough power to accelerate Earth's rotation measurably if such force were applied to our planet. Yet despite their violence, pulsars always settle back into their rhythmic ticking, their magnetic fields still beaming radiation into space with near-perfect regularity. It's a reminder that even in the most extreme environments, the universe has a way of self-correcting, though not without the occasional dramatic tantrum. These cosmic speed bumps aren't just curiosities, they're laboratories for physics we can't replicate on Earth. By studying glitches, scientists probe the behavior of matter at densities impossible to create in particle colliders, where atomic nuclei dissolve into a sea of quarks and gluons. Each hiccup is like a telegram from the heart of a dead star, carrying secrets about the fundamental forces that govern reality itself. And with every new glitch detected, we get one step closer to unraveling the mysteries of matter pushed to its absolute limits. Fact 19. White dwarf collisions, the universe's most catastrophic traffic accidents. Picture two burned-out stellar cores, each packing a sun's worth of mass into a sphere the size of Earth, hurtling toward each other at thousands of kilometers per second. These aren't just dead stars, they're ticking time bombs, and when they collide, the explosion rivals the brightness of an entire galaxy. But what makes these cosmic pile-ups so special isn't just their violence, it's how they've become the universe's measuring tape, helping us map the expansion of space itself. The drama begins with white dwarfs, the dense remnants of stars like our Sun. After exhausting their nuclear fuel, they shed their outer layers and shrink into Earth-sized embers, so dense that a sugar cube's worth of their material would weigh as much as an elephant. Most spend eternity cooling quietly unless they have a companion. In binary systems, two white dwarfs can orbit each other for billions of years, slowly spiraling closer as they radiate energy in gravitational waves. When they finally merge, the result is pure chaos. The lighter star gets shredded by tidal forces, dumping its material onto its partner in a superheated whirlpool. If the combined mass crosses a critical threshold about 1.4 times the Sun's mass, the carbon and oxygen in their cores ignite in a runaway nuclear chain reaction. What follows is one of the most predictable explosions in the cosmos, a Type I supernova. Unlike the messy deaths of massive stars, these detonations always release the same amount of energy, making them perfect standard candles for measuring cosmic distances. In the 1990s, astronomers used these explosions to make a shocking discovery. The universe's expansion isn't slowing down as expected. It's accelerating, driven by the mysterious force we now call dark energy. Without white dwarf collisions, we might never have uncovered one of the greatest mysteries in modern physics. But here's where it gets even wilder. Not all white dwarf mergers end in total annihilation. Some barely skirt that critical mass limit, triggering partial explosions that leave behind bizarre hybrid objects. Imagine a supernova that doesn't quite finish the job, leaving a zombie star called a superchandrasekhar mass remnant behind. Others might collapse directly into neutron stars, skipping the explosion entirely. These rarer outcomes are like cosmic failed fireworks, giving astronomers clues about the delicate balance between gravity and nuclear fire at the heart of these events. The aftermath of these collisions is just as fascinating as the explosions themselves. The expanding debris enriches the galaxy with iron, silicon, and other heavy elements, the building blocks of rocky planets like Earth. Some models even suggest our solar system might owe its existence to a nearby Type Ia supernova, whose shockwave triggered the collapse of the molecular cloud that birthed the Sun. It's a humbling thought. The same explosions that help us measure the cosmos might also have set the stage for life itself. What's truly mind-blowing is how common these events must be. While we've only observed a handful in progress, computer simulations suggest white dwarf mergers happen roughly once every century in a galaxy like ours. That means somewhere in the universe right now, two stellar corpses are circling each other in a deadly dance, destined to light up the darkness with a brilliance that transcends time and space. And with new telescopes scanning the skies every night, we're getting closer than ever to catching one of these cosmic smash-ups in action, a front row seat to the universe's most precise yet violent measuring tools. Fact 20. Microquasars, the scaled-down death rays of the galaxy. While quasars blast jets across billions of light-years from supermassive black holes, their smaller cousins prove you don't need cosmic titans to create astrophysical havoc. Imagine a black hole or neutron star just a few times heavier than our Sun, stealing material from a companion star and firing off plasma beams at nearly light speed. These aren't just compact powerhouses, they're miniature laboratories for studying the most extreme physics in our cosmic backyard. Take SS433, the first microquasar discovered in our galaxy and still one of the weirdest. Located about 18,000 light-years away in the constellation Aquila, this system consists of a black hole or neutron star orbiting a massive donor star. What makes it extraordinary are the twin jets spiraling outward like a cosmic corkscrew, processing so predictably that they complete a full twist every 162 days. The material in those jets races at a quarter the speed of light, glowing with X-rays as magnetic fields twist them into helical structures visible across wavelengths. The mechanics behind these mini-monsters mirror their larger quasar cousins, just compressed into a stellar package. As gas from the companion star spirals into an accretion disk around the compact object, friction heats it to millions of degrees. But unlike normal binary systems, microquasars channel some of that infalling material into focused beams perpendicular to the disk, accelerated by magnetic fields coiled tighter than a spring. The result, particle cannons so powerful they'd slice through planets if any wandered too close, all from a system smaller than our solar system. What's fascinating is how these small-scale jets help us unravel big mysteries. Because microquasars evolve over years rather than millennia, we can watch entire cycles of jet formation and collapse in real time. Their outbursts mimic the behavior of supermassive black holes, offering clues about how galactic-scale jets stay collimated over millions of light-years. Some even produce detectable gravitational waves when the compact object's spin axis wobbles, a phenomenon we've only begun to explore. The real surprise is how common these systems might be. While we've identified only a few dozen microquasars in the Milky Way, simulations suggest hundreds could be lurking undetected, their jets pointed away from Earth. Each one is a cosmic particle accelerator, a natural version of machines like the Large Hadron Collider, but operating at energies we could never achieve on Earth. And as our telescopes grow more sensitive, we're finding even stranger variants, like microquasars where the jets flicker on and off like a faulty cosmic flashlight, or ones where the compact object is a magnetar, its already intense beams supercharged by a magnetic field a quadrillion times Earth. SS-433 remains the crown jewel, though. Its twisting jets have been studied for decades, yet they still defy full explanation. Why do they precess so regularly? How do particles in the beams maintain such insane energies? Every answer leads to new questions, proving that sometimes the most explosive lessons come in the smallest packages. These stellar-scale jets remind us that the universe doesn't need supermassive black holes to unleash its fury, just a hungry, compact object and a star unlucky enough to orbit it. Fact 21. Galactic collisions, the universe's slow-motion car crashes. Picture two galaxies, each containing hundreds of billions of stars, drifting toward each other over billions of years until gravity locks them in a dance of destruction and creation. These aren't just cosmic mergers, they're the ultimate fireworks displays, where shockwaves trigger bursts of star formation so intense, they light up the darkness like celestial beacons. And here's the wildest part, our own Milky Way is on a collision course with its nearest neighbor, Andromeda, in a crash so epic it will rewrite the night sky forever. When galaxies collide, the chaos unfolds over timescales that dwarf human history. Stars rarely hit each other. The distances between them are too vast, but their orbits get scrambled like balls in a cosmic pinball machine. Gas clouds, on the other hand, slam together with enough force to collapse into nurseries of new stars. Take the Antennae galaxies, one of the closest and most studied merging pairs. Their long, streamer-like tails, stretched out by tidal forces, are studded with superstar clusters, each containing millions of newborn suns. The collision's shockwaves compressed so much gas and dust that these galaxies now produce stars 20 times faster than the Milky Way. It's a spectacle of creation born from destruction. What's fascinating is how these collisions sculpt galaxies into entirely new shapes. Spiral galaxies like ours, with their elegant arms, often transform into featureless ellipticals after a major merger. The violence disrupts their delicate structures, randomizing stellar orbits into bloated, football-shaped swarms. But sometimes mergers create unexpected beauty, like the Cartwheel Galaxy, a rare ring-shaped galaxy likely formed when a smaller companion punched through its center, sending a ripple of star formation outward like a pebble dropped in a pond. Now, let's talk about the elephant in the room, the impending collision between the Milky Way and Andromeda. 4 billion years from now, our galaxy's serene spiral arms will begin tangling with Andromeda's, their mutual gravity pulling them into a series of ever-tightening orbits. Computer simulations show the two galaxies will pass through each other multiple times before finally merging into a single, massive elliptical galaxy nicknamed Milkdromeda. The process will take another 2 billion years, during which the night sky, as seen from any surviving planets, will transform completely. Andromeda, currently a faint smudge in the constellation of the same name, will grow larger and brighter with each passing millennium until it fills half the sky. But don't brace for catastrophe. Earth will likely survive unscathed. The odds of our solar system getting ejected into intergalactic space are slim, and direct stellar collisions are virtually impossible. Instead, we'll witness a celestial light show unmatched in history, with newborn stars igniting across the sky and the combined glow of 2 trillion suns bathing our planet in an eerie, eternal twilight. The real casualty will be the Milky Way as we know it, its elegant spiral arms shredded and reformed into something new. Galactic collisions are more than just destruction, they're the universe's way of recycling. Without them, galaxies would run out of the gas needed to form new stars, freezing cosmic evolution in its tracks. And as we look out at distant mergers through telescopes, we're glimpsing our own far future. A reminder that even the mightiest structures in the cosmos are fleeting, destined to collide, merge, and transform in the endless dance of gravity. So the next time you gaze up at Andromeda, remember, it's not just a neighbor, it's our galaxy's future dance partner, waiting for its cue in the slow-motion ballet of the universe. Fact 22. Relativistic jets, nature's ultimate particle accelerators. Imagine a black hole so voracious it doesn't just consume matter. It spits some of it back out in beams of plasma moving at 99% the speed of light. These aren't just cosmic geysers, they're precision-engineered death rays, narrower than a solar system, yet stretching millions of light years into intergalactic space, carving through galaxies like a scalpel through silk. The physics behind these jets is as breathtaking as their scale. Near a black hole or neutron star, infalling matter doesn't just vanish quietly. It forms a superheated accretion disk spinning at nearly light speed and generating magnetic fields trillions of times stronger than Earth. Some particles get funneled toward the poles where magnetic fields coil like springs, launching them outward in collimated beams. Picture a cosmic fire hose powered by the energy of millions of suns, where electrons and protons are whipped to energies even our most powerful particle colliders can't match. What makes these jets truly mind-bending is how far they travel without dissipating. The longest known jet, stretching from galaxy M87, extends at least 5,000 light-years visible because it's pointed almost directly at Earth, making it one of the most studied cosmic particle beams. But some quasars boast jets stretching millions of light-years, far longer than their host galaxies. That persistence defies intuition. How do these beams remain so tightly focused over distances that dwarf entire galactic clusters? The answer lies in a phenomenon called magnetic confinement, where twisted magnetic fields act like an invisible barrel, preventing the jet's particles from scattering into the void. The energy in these jets is almost incomprehensible. A single one can outshine its entire host galaxy in radio waves, emitting as much power in seconds as the sun will over its lifetime. Some even produce superluminal illusions where material appears to move faster than light due to relativistic effects, like a cosmic version of a sonic boom. Yet for all their fury, relativistic jets are also cosmic sculptors. When they plow into intergalactic gas, they create shock waves that trigger or suppress star formation, essentially dictating how galaxies evolve over billions of years. Here's the twist: we've caught these jets in the act of changing direction. In 2017, astronomers watched a black hole's jet wobble like a spinning top, likely due to warped space-time near the black hole's equator. Others flicker unpredictably, hinting at turbulent feeding cycles where the black hole gorges on matter before belching out fresh plasma. These observations are like peering into the black hole's digestive system, revealing how even the most destructive forces in nature follow rules we're only beginning to decode. What's truly humbling is how these beams connect the infinitesimally small to the astronomically large. The same physics that governs particles in a lab accelerator electromagnetic fields, Lorentz forces. Shockwaves operates on scales so vast it takes light eons to traverse them. And with telescopes like the Event Horizon Telescope now mapping jet launch zones in unprecedented detail, we're closing in on one of astrophysics' biggest mysteries: how black holes, the universe's ultimate sinks of matter and light, somehow become its most powerful engines of creation. Fact 23. The Fermi bubbles, our galaxy's ghostly explosion remnants. Towering 25,000 light-years above and below the Milky Way center, these twin lobes of superheated gas and gamma rays are like cosmic bruises, evidence of a violent outburst that rocked our home galaxy sometime in the distant past. Discovered in 2010 by NASA, a Fermi Gamma Ray Space Telescope, these structures glow with the energy of 100,000 exploding stars, yet their origins remain one of the most tantalizing mysteries in modern astrophysics. The scale alone is staggering. Each bubble stretches halfway across the visible sky. If you could see them in gamma rays like a colossal hourglass carved into the fabric of the Milky Way. The gas within races outward at millions of kilometers per hour, hotter than the surface of most stars, while emitting high-energy radiation that paints them as faint, gargantuan silhouettes against the cosmic background. What's bizarre is how crisp their edges are, as if something punched through the galaxy's diffuse halo with surgical precision, leaving behind structures sharper than anyone predicted. So what caused this ancient cataclysm? The prime suspect sits at the very center of the Milky Way, Sagittarius, a star, our resident supermassive black hole. One theory suggests it went through a feeding frenzy millions of years ago, gorging on a huge cloud of gas or even a star cluster. As material spiraled inward, colossal magnetic fields could have funneled some of it into bipolar jets, blasting the bubbles outward like a cosmic pressure washer. Supporting this idea are the Fermi cocoons, smaller gamma-ray structures found near the galactic center, possibly remnants of smaller, more recent outbursts from the same hungry black hole. But there's a competing explanation, a frenzy of star formation so intense, it essentially blew the roof off the galaxy. In this scenario, a wave of supernovas, hundreds or thousands exploding in quick succession, could have pumped enough energy into the surrounding gas to inflate these massive structures. The Milky Way's central regions are indeed crammed with young, massive stars that live fast and die violently, making this a plausible alternative. Here's where it gets even stranger. Some researchers propose the bubbles might be the combined result of both processes, black hole activity and stellar fireworks, occurring in overlapping epochs. Or perhaps they're evidence of something even more exotic, like dark matter particles annihilating each other near the galactic core. The truth is, we're still piecing together the clues. What makes the Fermi bubbles so fascinating isn't just their size or energy, it's how recently we discovered them, hiding in plain sight all this time. They're a reminder that even our own galaxy, which we've mapped and studied for centuries, can still surprise us with relics of its explosive past. And as new telescopes probe their structure in greater detail, we're inching closer to solving the puzzle of what, or who, lit the fuse on this cosmic bomb millions of years ago. Fact 24. Fast radio bursts, the universe's most cryptic Morse code. These fleeting blasts of radio waves last just milliseconds, yet pack the energy of 500 suns, beamed across billions of light years from galaxies far beyond our own. Discovered by accident in 2007 while sifting through archived pulsar data, these bursts arrive without warning, vanish in the blink of an eye, and leave behind more questions than answers. But one in particular, FRB 1211, defies all expectations by doing something extraordinary. It repeats. Picture a cosmic lighthouse that flickers at random intervals, sometimes silent for months, then suddenly erupting in a flurry of signals. That's FRB 1211, the first repeating fast radio burst ever detected. While most FRBs are one-off events, likely caused by catastrophic collisions or implosions, this enigmatic source near a dwarf galaxy 3 billion light-years away pulses sporadically, as if something or someone is flipping a switch. The pattern is so erratic that astronomers have spent years searching for clues in its cadence, wondering if it's a malfunctioning alien transmitter or the death throes of an exotic stellar remnant. The leading theories sound like sci-fi plotlines. One suggests highly magnetized neutron stars called magnetars, their crusts cracking under unimaginable strain, releasing abrupt quakes of radio energy. Another proposes bizarre stellar collisions, white dwarfs smashing into neutron stars, or black holes tearing through dense plasma clouds. But the repeating bursts throw a wrench into these explanations. How could a cataclysmic event explode over and over? Some researchers speculate it might involve a neutron star orbiting a massive companion, its magnetic field lines snapping and reconnecting like cosmic rubber bands with each close pass. Then there's the sheer distance problem. Fast radio bursts traverse half the observable universe, their signals distorted by the sparse electrons floating between galaxies. This intergalactic fog actually helps astronomers weigh the missing matter in the cosmos, like using static on a radio to map invisible terrain. Yet no one knows how these bursts are produced with such intensity. If we scaled their energy to something familiar, it'd be like microwaving a bowl of oatmeal with the entire power output of the sun for 30 milliseconds. What makes FRBs truly tantalizing is how new they are to science. The first one was only recognized in 2007, hidden in data from 6 years prior. Now, new telescopes like CHIME in Canada are detecting dozens monthly, each a puzzle piece in understanding the universe's most energetic short-lived events. And with every repeating burst like 1211, the mystery deepens. Are these natural cosmic phenomena, or could they be against all odds technological? The truth is, we're still tuning our receivers to the universe's weirdest radio station, waiting for the next burst to crackle through the static and rewrite the rules. Fact 25. Dark matter annihilation, the universe's most elusive light show. Hidden in the vast cosmic shadows, particles we can't see or touch might be colliding in explosions of pure energy, producing gamma rays like ghostly fireworks in the void. This isn't just theoretical. Scientists are hunting for these faint signatures, hoping to catch a glimpse of the invisible stuff that makes up 85% of the universe's matter. The mystery begins with dark matter itself. Unlike stars or gas, it doesn't emit, absorb, or reflect light. We only know it exists because its gravitational pull tugs on galaxies, bending space like an unseen hand pressing on a cosmic trampoline. But if certain theories are correct, dark matter particles could occasionally slam into each other, annihilating in bursts of gamma rays, the universe's highest energy light. Picture two phantoms passing through each other in the dark, then poof, vanishing in a flash of radiation detectable across the cosmos. The search for these signals has led astronomers to some unlikely places. Dwarf galaxies orbiting the Milky Way, like Draco or Sculptor, are prime hunting grounds. These faint, ancient systems are teeming with dark matter, but have few stars or gas clouds to muddy the signal. Then there's the center of our own galaxy, where dark matter is thought to pile up like snowdrifts around the supermassive black hole. Telescopes like NASA's Fermi Gamma Ray Space Telescope scour these regions for unexplained gamma ray excesses, puzzling glows that just might be the smoking gun of dark matter's self-destruction. But proving it isn't easy. Other cosmic phenomena like pulsars or gas clouds can mimic these signals. That's why scientists look for specific patterns in the gamma ray's energy distribution, clues that point to dark matter's unique fingerprint. Some theories predict these annihilations should produce a smooth spectrum, while others suggest sharp spikes at certain energies. It's like trying to identify a song played in a crowded room by listening for one instrument's melody. The stakes couldn't be higher. Catching dark matter in the act wouldn't just confirm its existence, it would reveal what it's made of. Is it WIMP, weakly interacting massive particles, actions, or something even stranger? Each possibility would leave a distinct mark in the gamma ray data, potentially unlocking mysteries that have puzzled physicists for decades. And with next-generation telescopes like the Cherenkov Telescope Array coming online, the hunt is heating up. What's fascinating is how these invisible explosions could shape the cosmos. If dark matter annihilations were more common in the early universe, they might have influenced how galaxies formed, or even seeded the first structures with pockets of heat. It's a reminder that the universe's greatest dramas often play out in the dark, unseen but undeniable. And every unexplained gamma-ray photon brings us one step closer to pulling back the curtain on the universe's best-kept secret. Fact 26. The Great Attractor, the universe's most unsettling blind spot. Imagine a gravitational vortex so powerful, it's tugging thousands of galaxies, including our own Milky Way, toward it at nearly 2 million kilometers per hour. This cosmic supervillain lurks somewhere in the constellation Centaurus, but here's the catch: we can't actually see it. The entire region is hidden behind the Milky Way's dusty, star-choked disk, forcing astronomers to study it like detectives piecing together clues from a crime scene obscured by smoke. The mystery began in the 1970s when scientists noticed something bizarre about the local universe's motion. Galaxies weren't just drifting apart due to cosmic expansion. They were all streaming toward the same patch of sky like leaves caught in a celestial whirlpool. The culprit, a gravitational anomaly packing the mass of tens of thousands of Milky Ways, dubbed the Great Attractor, but every attempt to observe it directly hit a wall, literally. Our galaxy's central bulge blocks the view, absorbing visible light and radio waves like a cosmic fog. So how do we study something invisible? By observing its gravitational fingerprints on everything around it. Astronomers use redshift surveys mapping galaxies' movements in 3 dimensions to trace the Great Attractor's pull like ripples spreading across a pond. X-ray telescopes peer through the dust, revealing galaxy clusters like Norma Cluster, believed to be part of this larger structure. Even more telling is the dipole repeller, a vast cosmic void on the opposite side of the sky that's pushing us toward the attractor, as if the universe itself is herding galaxies into this gravitational sinkhole. The scale of this anomaly is staggering. The Great Attractor's influence extends over hundreds of millions of light-years, shaping the motion of galaxies as far away as the Hydra-Centaurus supercluster. Some researchers believe it might be just one piece of an even larger structure, the Laniakea supercluster, a filamentary web of galaxies spanning 500 million light-years, with the attractor acting as its gravitational anchor. Here's the twist: the Great Attractor might not even be the end game. Beyond it lies the Shapley supercluster, an even mightier concentration of mass pulling the attractor itself, and us along with it, in a cosmic chain of gravitational puppetry. It's a humbling reminder that no matter how grand our galaxy seems, we're just a speck caught in a tug of war between invisible giants, drawn toward mysteries still waiting in the dark. Fact 27. The Boat Gamma Ray Burst, the brightest cosmic explosion ever recorded. On October 9, 2022, a gamma-ray burst designated GRB 221009 erupted from the constellation Sagitta, slamming into detectors across our solar system with such intensity. It blinded orbiting telescopes and saturated instruments designed to study these very events. This wasn't just another burst, it was a cosmic flashbulb so powerful, astronomers calculated it carried more energy than our Sun will emit across its entire 10 billion-year lifetime, all compressed into a few hundred seconds. What made this explosion, nicknamed the BOAT, brightest of all time, so extraordinary wasn't just its raw power, it was the perfect alignment of factors that made it visible to us. The burst originated relatively close by, just 2.4 billion light-years away, a stone's throw in cosmic terms for such phenomena. But more crucially, its narrow, pencil-thin jet happened to be pointed almost directly at Earth, funneling its full fury straight into our line of sight. Imagine standing in front of a fire hose blasting at near light speed while every other observer gets just the spray's mist. That's the vantage point we accidentally stumbled into. The numbers defy comprehension. For about 10 minutes, GRB 221009, a flooded space with high-energy photons, some reaching energies of 18 tera-electronvolts, so extreme they triggered atmospheric phenomena normally seen only when cosmic rays hit Earth's upper atmosphere. The burst's initial flash was so bright, it overwhelmed detectors on NASA's Fermi Gamma Ray Space Telescope, forcing scientists to reconstruct the data from the instrument's side sensors never intended for such measurements. Even spacecraft orbiting Mars and Venus picked up the blast, marking the first time a gamma-ray burst was detected from multiple points in the solar system simultaneously. Yet the boat's true significance lies in what it revealed about these cosmic catastrophes. Follow-up observations showed something unexpected. Despite its record-breaking brightness, the burst didn't leave behind an unusually large supernova or black hole. Instead, its power likely came from an exceptionally efficient jet, one that converted nearly all its energy into focused radiation rather than dispersing it in all directions. It's like comparing a laser to a light bulb. Both might use the same energy, but one concentrates it into a beam capable of punching through steel. The aftermath was just as puzzling. As the jet plowed through interstellar gas, it created shock waves that glowed in X-rays for weeks, an afterglow that faded much slower than models predicted. This lingering radiance suggests the surrounding environment might have been unusually dense, perhaps because the progenitor star sat in a stellar nursery packed with gas and dust. Some researchers even speculate the burst's parent star was chemically pristine, made mostly of hydrogen and helium from the early universe, which could have influenced how it collapsed and exploded. Here's the chilling part: if a burst this bright happened within our own galaxy, even thousands of light years away, its radiation could have stripped Earth's ozone layer, triggering mass extinctions. In fact, some scientists theorize a past gamma-ray burst might explain the Ordovician extinction 450 million years ago, when marine life vanished mysteriously. The boat serves as a reminder that the universe doesn't just operate on scales beyond human experience. It occasionally flexes power so immense, even detectors built to study such events can barely handle it. But beyond the shock and awe, GB 221009 gave astronomers something priceless: a once-in-a-millennium laboratory to test theories about stellar deaths, jet physics, and the birth of black holes. Its light carried fingerprints of heavy elements forged in the explosion, clues about magnetic fields in distant galaxies, and even subtle distortions caused by passing through the cosmic web of dark matter. For a few brief hours, this flash from the distant past became the brightest thing in the gamma-ray sky, a temporary beacon illuminating secrets we're only beginning to decode. Fact 28: Wolf-Rayet stars, the cosmic equivalent of a time bomb with its fuse already burning. These aren't just massive stars, they're stellar powerhouses so unstable they're literally tearing themselves apart while still shining. Picture a sun 20 times more massive than our own, wrapped in a hurricane of its own expelled gas, screaming through space at speeds topping 5 million miles per hour. These stars don't just burn, they rage, shedding entire solar masses worth of material in winds so fierce they could strip a planet to its core in minutes. What makes Wolf-Rayet stars stand out isn't just their violence, it's what's lurking beneath the chaos. Peel back those furious stellar winds and you'll find a core so hot it fuses elements at a breakneck pace, racing through its nuclear fuel in mere millions of years instead of billions. The surface temperatures soar above 90,000 degrees Fahrenheit, so scorching that these stars glow blue-white like a welding torch, ionizing the surrounding gas into eerie nebulas that shimmer like cosmic ghosts. The real drama begins when these living bombs near the end of their short, spectacular lives. Unlike ordinary stars that fade quietly, Wolf-Rayet stars are primed for catastrophe. Having already blown away their hydrogen envelopes, they're left with exposed cores of helium, carbon, and oxygen elements normally buried deep inside a star. This sets the stage for one of two possible finales: a supernova so bright it could outshine entire galaxies, or a gamma-ray burst so focused it could sterilize planets light years away. Take the star WR104, for example, a celestial pinwheel spinning in the constellation Sagittarius. Its winds collide with those of a companion star, creating a dazzling spiral of dust visible from Earth. But this beauty is deceptive. WR104 is a ticking time bomb, likely to end its life as a gamma-ray burst. If its poles align with Earth when it explodes, the resulting beam of radiation could deliver more energy to our atmosphere than a full-scale nuclear war, though thankfully we're safely out of the line of fire. The aftermath of a Wolf-Rayet star's death is just as dramatic. Their explosions seed the cosmos with heavy elements like oxygen, neon, and iron, the building blocks of future stars and planets. Some even collapse directly into black holes without the traditional supernova fanfare, vanishing from the universe like a magician's trick. It's a reminder that destruction and creation are intertwined in the cosmos, and that even the most violent stars play a vital role in shaping the universe around us. What's truly humbling is how rare these stellar monsters are. Of the hundreds of billions of stars in our galaxy, only a few hundred Wolf-Rayet stars have been identified, each one a fleeting spectacle, burning twice as bright but half as long. Their very existence defies the steady rhythms of stellar evolution, proving that sometimes the universe favors fireworks over longevity. And with every new observation, we're piecing together the final, explosive chapters of these living bombs before they rewrite the night sky in one last, blinding flash. Fact 29. The Chicxulub impact, the day the sky fell. 66 million years ago, a mountain-sized asteroid, traveling faster than a rifle bullet, slammed into what's now the Yucatan Peninsula with the force of 100 million megatons of TNT, 10 billion times more powerful than the atomic bomb dropped on Hiroshima. This wasn't just an impact, it was an atmospheric detonation that unleashed firestorms, mega tsunamis, and a global winter so severe it wiped out 75% of Earth's species, including the non-avian dinosaurs. The explosion itself vaporized rock, carving a crater 110 miles wide and 12 miles deep, while the shockwave liquefied the ground for hundreds of miles, turning solid Earth into a churning sea of molten debris. To grasp the scale, imagine stacking every nuclear weapon ever built, then multiplying that energy by 1,000,000. The initial fireball reached temperatures hotter than the sun's surface, igniting wildfires across continents. Meanwhile, debris ejected into space rained back down globally, superheating the atmosphere until it literally glowed like an oven coil. But the real killer was the aftermath. Sulfur from vaporized rock mixed with water vapor, forming a thick blanket of sulfuric acid clouds that blocked sunlight for years. Photosynthesis collapsed, food chains disintegrated, and temperatures plummeted by as much as 50 degrees Fahrenheit. It was less an extinction event and more a planetary reset button. What's terrifying is how common such threats remain. The solar system is littered with cosmic debris, asteroids, comets, and rogue planet fragments, many still undiscovered. In 2013, the Chelyabinsk meteor exploded over Russia with the energy of 30 Hiroshima bombs, injuring 1,500 people. It was just 65 feet wide. Chicxulub's asteroid, at least 6 miles across, NASA Planetary Defense Coordination Office now tracks over 27,000 near-Earth objects, with hundreds added monthly. While none currently threaten civilization, the odds aren't zero. Statistically, a Chicxulub-scale event strikes Earth every 100 million years, meaning we're technically overdue. Here's the cosmic irony. These apocalyptic impacts are also engines of renewal. Without Chicxulub, mammals might never have inherited the Earth. That extinction opened niches for our ancestors to thrive, setting the stage for humans to eventually walk the planet. The same violence that erases life also reshapes it, a pattern we see across the universe, from supernovas scattering heavy elements to galactic collisions birthing new stars. Yet Chicxulub's legacy isn't just ancient history. It's a warning. Today, telescopes like Pan-STARRS scan the sky nightly, while missions like DART test deflecting asteroids kinetically. The challenge isn't just spotting threats, it's acting in time. A 6-mile-wide asteroid tomorrow would give us decades, maybe just years, to respond. The universe doesn't care about our calendars, but for now, that crater in Mexico stands as a monument to our planet's resilience, and a reminder that the next cosmic bullet could already be inbound, silent and unseen, somewhere in the dark. Fact 30. The heat death, the universe's silent and inevitable fade to black. Forget explosive finales. This is the cosmos winding down like an unwound clock, where every star flickers out, every black hole evaporates, and space itself stretches into an infinite frozen void. Across trillions upon trillions of years, the universe won't so much end as exhaust itself, dispersing energy so thinly that not a single spark remains to light the darkness. It's the ultimate triumph of entropy, where even time loses all meaning. To grasp this slow-motion apocalypse, imagine a cup of coffee left forgotten on a counter. At first, steam rises in swirling tendrils, warmth radiating outward, but eventually, it cools to room temperature, its heat molecules dissipated beyond recovery. Now scale that up to cosmic proportions. Stars, the engines of creation, will one by one burn through their fuel, collapsing into white dwarfs that dim like dying embers. Galaxies, untethered by dark energy's relentless push, will drift apart until each is marooned in its own private horizon. Even black holes, those seemingly indestructible gravity traps, aren't safe. They'll leak away through Hawking radiation, vanishing in weaker and weaker puffs of particles over timescales so vast, a billion years feels like a blink. What makes this fate so unsettling isn't its violence, it's the absence of it. Contrast this with the fiery cataclysms we've explored. Supernovas shredding stars, black holes colliding in space-time rending mergers, gamma-ray bursts sterilizing galaxies in seconds. Those are cosmic screams. The heat death is a whisper. Thermodynamics guarantees it. Energy always spreads out, never concentrating again once equilibrium is reached. The universe will become a sparse soup of particles so far apart, no two will ever interact again. No new stars will ignite. No planets will form, just a featureless expanse, colder than absolute zero, darker than the deepest void. Yet there's a strange beauty in this bleak outcome. Every explosion we've witnessed, every supernova, kilonova, or quasar jet, temporary as they are, has been a battle against this inevitable end. Stars burn bright to stave off collapse, black holes feast to delay evaporation. The universe, in all its chaos, is fighting a losing war against entropy, and every brilliant detonation is a fleeting act of defiance. Even humanity's existence is a statistical miracle, a brief spark in the cosmic night before the cold sets in. But here's the twist: the heat death might not be the final chapter. Some theories suggest quantum fluctuations could spawn new universes in the emptiness, birthing fresh cosmic cycles from the void. Others propose that advanced civilizations, if any survive, might harness black holes as energy sources to outlast the gloom. Or perhaps the universe holds secrets we've yet to uncover, hidden physics that could rewrite this seemingly inescapable fate. For now, the heat death remains the ultimate checkmate in nature's game, an end where the cosmos doesn't bang or whimper, but simply forgets how to be anything at all. From supernovas scattering the elements of life across the cosmos to hypernovas firing death rays capable of sterilizing galaxies, we've journeyed through the universe's most explosive spectacles, where destruction and creation collide on incomprehensible scales. These aren't just fireworks, they're the engines reshaping reality itself. Gamma-ray bursts beam more energy in seconds than our sun will emit in its lifetime. Kilonovas forge gold in stellar collisions, and quasars outshine galaxies from the dawn of time. Even black holes, those cosmic vacuum cleaners, become artists when they shred stars into glowing ribbons of light or launch jets that pierce intergalactic space for millions of years. Consider this: every atom in your body was forged in the heart of a dying star or a cataclysmic collision billions of years ago. The iron in your blood, the calcium in your bones, these are the ashes of explosions so vast they defy imagination. And the universe isn't done yet. Right now, stars are dying in spectacular supernovas. Neutron stars are spiraling toward collisions that will shake space-time. And rogue black holes drift unseen, waiting to rewrite the fate of any system unlucky enough to cross their path. But here's the humbling truth: we've barely scratched the surface. What other violent wonders lurk beyond our current understanding? Could there be explosions powered by dark matter, or quantum detonations rewriting the laws of physics itself? The cosmos loves surprises like the Fermi bubbles, those ghostly remnants of a Milky Way eruption we didn't even know happened until recently. So tell us, which fact left you in awe? Was it the magnetar flare that compressed Earth's atmosphere, or the boat gamma-ray burst that blinded our telescopes? Drop your favorite in the comments, and if you're hungry for more cosmic chaos, hit subscribe. The universe isn't just violent, it's alive with mysteries waiting to be uncovered, and we're just getting started. After all, in a cosmos where even vacuum decay could rewrite reality in an instant, one question remains: what unimaginable explosions are still lurking in the dark, just waiting for us to look